Hello, this is Mr. Win, and this video is about inverses. When you find the inverse of something, you basically reverse everything. All x's and y's will switch or flip places. Doing this will also switch the domain range. For example, here's a table. We have 3 points, 1, -2, 2, 5, 4, -1. So for this, the domain, the x's is 1, 2, 4. In the range, the y's are -2, 5, -1. I put in the correct order here. When I flip it, now everything's backwards. So now all the x's are -2, 5, -1. All the y's are 1, 2, 4. So the old domain became the new range, and the old range became the new domain. If you put these on the graph, here's the two pictures. You can see two triangles here. The graphs will always be mirror images of each other reflected across the diagonal line y equals x. So that basically means if you fold it across the diagonal line, they'll overlap perfectly. When we have a function named f of x, we call its inverse f inverse of x. So that's not a -1 exponent. That doesn't do anything. It's just the name of something. Just like when we say g of x, the equation is named g. This is the equation named f inverse. Alright, to algebraically solve for an inverse, we'll do 3 steps. Step 1 is get the equation into y equals form. This is a temporary placeholder to make our work look easier. Step 2 is switch all x's and y's. Do not move any numbers or change any signs. And then step 3, solve for the new y, and don't forget to change the temporary y back to its real name, but now inverse. So here's an example. Find the inverse of f of x equals 2x minus 5. So step 1, put into y equals. All I'm going to do is change this f of x into y. Step 2, switch every x and y. So this y becomes x, this x turns to y. Do not change the positive 2, do not change the negative 5. Step 3, solve. So to get y by itself, you move the 5 over by adding it. Then get rid of this 2 by division. Then remember, this y was not there originally. We put it there temporarily. We're going to change it into f of x, but now f inverse of x. And I like the big answer like that, but you do have the option of splitting this fraction into multiple fractions. You do every numerator at the bottom, so you do x over 2 plus 5 over 2. Now remember, if you split this up to multiple fractions, do check if each one does reduce. Then some kids don't like x on top of a fraction, they like it beside a fraction, so that's the same thing. So all 3 of these answers are right. So let's check the graph. So the red line is the original f of x, 2x minus 5, and the blue line is the one that we just found, the inverse, x plus 5 all over 2. Is that a reflection over this diagonal line y equals x? Yeah, because I fold it. They'll match perfectly. They are mirror images. So if you ever do a composition with a pair of inverse functions, they will reverse or undo each other, getting you back to what you started with. So let's give it a try using the pair of inverse functions we just found. Find the composition of f inverse of 9 and f inverse composed with f of 9. Alright, so here's the two equations. First, I'm going to find f of f inverse of 9. So I wrote it the nice way. Remember, this 9 only goes to the last thing, f inverse. So to find f inverse of 9, I'm going to go to equation f inverse this and plug in 9 for every x. So 9 plus 5 over 2, that's 14 over 2, that's 7. So this gets turned to 7. Now I'm going to find f of 7. I'm going to go to equation f, plug in 7 for every x. So 2 times 7 minus 5, that's 14 minus 5, that's 9. Alright, so notice we got back to this 9. So if you think about it, if I plug in 9 into the equation here, for x, I get a y value or f inverse value of 7. And inverse is you flip the point, so shouldn't this be 7, 9? Answer is yes. So if you plug in 7, get 9, you plug in 9, you get 7, and you plug in 7, you get back to 9. So they undo each other, flip-flop. Same idea here, f inverse of f of 9 this time. So I wrote the nice way. I'm going to find f of 9 first, then plug that answer into f inverse. F of 9 means go to equation f, plug in 9 for x. 2 times 9 is 18, 18 minus 5 is 13. So that goes here. So now I'm going to find f inverse of 13. 13 plus 5 is 18, 18 by 2 is 9. So got back to the same 9. Whatever you plug in, you get back, because they undo or cancel each other out. So here, we first started 9 into the original to get 13, and if you inverse that, of course, this will be 13 comma 9. So plug in 9, get 13, plug in 13, get back to 9. Alright, you will notice when composing with inverses, it is the one-time order does not matter for compositions. Alright. Once we realize that a composition of inverse functions undo each other, we can then use that fact to our advantage to test if random functions are inverses or not. So we just need to check if f of f inverse of x comes to x, and f inverse of f of x comes back to x. And what are you plugging here? It goes in. So it could be 9 to 9 or 20 to 20, but we just put x for variable. Any x, anything comes back to the same thing. And officially must check both orderings. So let's officially verify that these two are inverse of each other. So first I'm going to find f of f inverse of x. So I wrote the nice way. I'm going to plug in x into the equation f inverse for x. Well, you put x in for x, it does not change. So it looks just like this. Now to find f of this, I'm going to go to equation f and plug in x plus 5 for every x. I need to do some side work here. So that's what it looks like. So this x right here turns to that fraction. Well, look, when you have fraction times multiplier and the multiplier matches the denominator, it can just cancel out. It just comes to the top. So it's x plus 5 minus 5 plus 5 minus 5 cancel out. It's just x. So this x will turn to the x. So look, we got back the x. We're good. Let's try the other way. F inverse of f of x. So I wrote the nice way. I'm finding f of x first. If I go to equation f and plug in x for x, it does not change. So it's going to turn to this. Now I'm going to plug that 2x minus 5 for x in the inverse equation. So hopefully you notice all we're doing is plugging the equation into x over here, then this whole equation for x over here. So here I'm going to do some work. So this top x turns to 2x minus 5. The parentheses does not matter, so the negative 5 plus 5 combined. So I just have 2x over 2, which reduces to x. So we do get x back. So these two are indeed inverses. Alright, next problem. So remember, to be a function, the graph must pass the vertical line test. That means each x cannot be used more than once. We really only care about the inverse if the inverse is a function too. And not every graph has an inverse that is a function. So let's take a look at our parent quadratic function, f of x equals x squared. So here's the graph, y equals x squared. It's the parabola. Right? Does the reflection over y equals x pass the vertical line? So this got reflected over this diagonal line to this blue sideways parabola here. Does this pass the vertical line test? Answer is no, it doesn't. So how can we tell if a function will have an inverse first, inverse or not, without drawing the full reflection over y equals x first? So and the answer to that is the horizontal line test. Right? So since inversing reverses or flips all x's and y's, we can't have the y's being used more than once either, since they're going to be new x's. And that's how they express the vertical line test. So if the original graph passes the horizontal line test, it will have an inverse function. Alright, so this fails. If I draw a horizontal line test here, it touches twice right there and right there. If I draw right here, it touches twice right there and there. Alright, absolute value functions and polynomials of even degree only have no inverse function because they all fail the horizontal line test. But there is a trick to help them have one. This trick is called restricting the domain. If we can ensure that there are no y's being repeated, that means they will pass the horizontal line test. We just have to erase or ignore the left half or right half of the graph. So let's take a look. So here's the graph. If I only use the domain x is greater than or equal to 0 for the original graph, that means I don't care about this left side. It's gone. Alright, then I only have the right half of the parabola. Now it will pass the horizontal line test because there's no repeat y's. Alright, the blue graph is the inverse of the right half of the parabola. So if I reflect this part only over the diagonal line, you do get this. Alright, same thing over here. If I only use the domain x is less than or equal to 0 for the original graph, so the left half, so this right part's gone. Alright, then I would have only the left half of the parabola. The blue graph is the inverse of the left half of the parabola. So if I reflect this over the diagonal line, of course I will get this. So that would be the inverse. Now if you're curious what's the inverse of a quadratic, let me show you the work. So step 1, make it y equals form. Step 2, switch x and y. Step 3, solve for y. Well, to get y by itself, create the square power, so I have square both sides. And then make sure you change this y back to its real name, so it's f inverse. So the inverse of a quadratic, mathematically or algebraically, appears to be a square root graph. So this is a square root graph right here. It's going up, it's positive coefficient, a is not negative. And then over here, a is negative, it's a flipped upside down square root. So if you need the positive half of a quadratic, use the positive square root. If you need the negative half of a quadratic, use the negative square root. Sometimes you see a plus or minus in front of the square root. Alright, one more problem. Let's do a complicated one. If m of x equals 7x minus 4 all cubed plus 8, find its inverse, m inverse x. So step 1, make it y equals form. Step 2, switch x and y. Do not change the numbers or signs or anything. This stayed positive 7, this stayed negative 4 on the inside, this stayed positive 8. Step 3, solve for y. So it's always the same 3 steps, but the third step, the solving part, might take longer than others. So to get this by itself, to get y by itself, you have to move this 8 first by subtracting it. Then I get rid of the 7 by dividing by it. Then you get rid of cube power by cube rooting both sides. Then you get rid of this 4 by adding it, and this 4 is outside the cube root, it's not being cube rooted. And then last, change this y back to its real name, so m inverse of x. That's it. Hope you enjoyed the video. Make sure you ask any questions. Thanks for watching. Bye.